Hello and welcome to another one of D's ADD videos. Today we're going to look at the example of finding the arc length of this function from in between these two x values. If you remember, the quick concept was we're looking for the distance between two values. There's the basic formula where it's 1 plus the derivative squared dx or dy depending on what type of function you're given. If you're given a function that's in terms of x, like this one here, then you use this formula where it's dy dx squared dx. If you're given in terms of y, then these are y values and this becomes dx dy. Okay? Whereas these are x values and that's dy dx. All right, so here we have this function. Actually, I should add the line y equals 0 just to make it a little easier to deal with. Just a quick sketch of the graph. You should remember that this is a parabola laying on its side. So there is the parabola. And then we're going between 1 and we're going between 2 x values. So we're trying to find this region of the curve right there. Okay? So let's set up our integral. The integral could be done, since this is in x values, you can do one of two integrals. I'll just set it up both ways. First one is going to be from 1 to 2, and then you would have to do the function in terms of x would have to get solved, so we'd square root both sides and we get plus or minus the square root of x equals y. The plus root x is the top half, the negative root x is the bottom half of this graph. And since we're dealing with the y equals 0, or I should have had y is greater than 0, I apologize. To restrict it to the arc length up here. Okay? Otherwise, this function has this region as well that we would have to account for if I didn't have that restriction. But equal to 0, that would be more of a for a volume of revolution or area of surface revolution or something like that. So back to the derivative of the root x. If y is equal to x to the 1/2, which is root x rewritten, dy dx would be 1/2 x to the negative 1/2. The negative exponent tells us to bring it back down, so that would be your derivative. And it would have to be squared. Okay? And then that would be dx at the end of that one, because we did dy dx. Alright? Now it's just a matter of algebra and integrating. Let's see if we can get this done really quick. Hopefully it's not too bad an integral. 1 over 4 when we square the 2, and the square root of x squared is x dx. So here I would find a common denominator of 4x, which would give me 4x plus 1 on the top. And that's still the integral from 1 to 2 dx. So at this point, let's see, is this a u sub? No. Oh, this might be a trig sub from the previous step. I think that's how you would do that one. I don't like the way that's looking, so I think it would have been easier to do a dy. You can see it's easier in some cases to do one or the other. Or we could have done the integral. Now I can't use 1 and 2 because those were x values, so I'd have to plug into my function to figure out what the corresponding y values are. So when x is 1, the square root of 1 is 1. And then when x is 2, the square root of 2 is root 2. So those would be my smaller and larger y values, and then I'd have the derivative of this is 2y, a lot easier to deal with. Dx dy is 2y. So we have 1 plus 2y squared dy. Now I'd much rather do this trig sub than the other one because that was nasty with fractions and randomness. So I'll go ahead and finish this one out for you. So we have root 1 plus 4y squared. You go off to the side and you do your substitution. U squared is 4y squared. I guess you could have just looked at it here. 4y squared, so u is 2y. And then a squared is 1, so a is 1. So then what you do is you set up your relationship. Because it's a plus sign and they're squared, it's u equals a tangent theta is a general relationship that we have here. So then at that point you plug in 2y equals 1 tan theta. Divide both sides, y equals 1/2 tan theta. And then dy would be the derivative, which is 1/2 the derivative. Ooh, that should be just tan theta. Getting ahead of myself there, sorry. Secant squared theta d theta. And then you would plug in, making this in terms of, this was dy, theta, so it would be 1 plus 2y is equal to tangent theta, right, if I remember correctly. Yes, so it would be tangent theta. And then dy was 1/2 secant squared theta d theta. Deep breath. All right, so we know that at this point we can use our identity, Pythagorean identity, that's secant squared theta, and we're square rooting that, which this annoyingly is going to be an integration by parts. So you can see the actual arc length is not too tedious. What's tedious is a resulting integration. Bring your constant out in front, times secant squared theta d theta. So because this problem is not about integration by parts, I'm going to pause this, do the integral, and then come back to it. Okay, that was a little longer than I thought it was. I need to work these examples out before I make them up, or after I make them up. So the integral of secant cubed is integration by parts. You can take this and break it up into two terms. Okay, there's a secant squared, and why we choose secant squared for dv is because you can integrate that real easily and get tangent theta. And then u becomes secant theta. The thing about this one is that it's one of those that repeats until you get the answer in your problem. So, or the problem in your answer, sorry. I'm dyslexic, it's getting late. So, take the derivative to find du, integrate to find v. This is the formula, plug in chug. And when you do so, you're going to get this step there. And then you combine your two tangents to get tangent squared, and then you use the even rule for tangent that says that you turn that into secant squared minus 1 and then distribute, and then you see all of a sudden, look at that. That's what we started out with, and it's in our problem. So what you do is you integrate those individually, separate them, okay, distribute that 1/2 through. And what I've done is I rewrote the problem in red. That was what we started out with. These are the first two parts of the answer. And then this is the part that shows up. Let me zoom out so you can see it a little bit better. Okay, so here's the original problem. Here's the first part of the answer. And then I moved that over here. and then that one went there. I know the integral of secant. Instead of doing the u substitution it requires, it's easier just to memorize this answer. It's the natural log of secant plus tangent. This secant, though, however, gets added to the other side because they're like terms, and we don't want to go through the process of integration by parts again, only to end up here again. So we add it over, just like we would add an x over to another x, combine the numbers in front. 1/2 plus 1/2 is 1. So that's where that is. And then this is what's left. The integral of secant is this. Again, memorize that. And I put a plus c there because I'm just doing the general integral. I didn't put the bounds in terms of theta, right? You can change the bounds using your substitution. So if I would have gone to 2y equals tangent theta, for instance, and I plug in a 1, I would have tangent theta equals 1 or arctan of 1, and that would have been up here. Then I could have not used a plus c, but this is easier for me. So if you remember in trig sub, you then have to use your relationship that I wrote up here to draw a triangle. You'll know this side and this side, and you use Pythagorean theorem to find that side. And then when you plug in for these expressions using that triangle, you come up with this. I simplified a little bit, then you would plug in root 2 everywhere and plug in a 1. I'm not going to bother with that. That's not the concept here. That's not what we're trying to learn. We're trying to learn the arc length. And even this integration was just a little friendly review of integration by parts. So you can see the setting up was not too bad. It's the integration that's going to get you. All right. So if you don't have a good foundation, your house will fall. So make sure you got that integration down pat. This is a great final exam question because, or an exam question because you're testing on arc length concept. You're also testing on trig substitution, and then you're doing integration by parts, and a weird integration by parts at that. Okay, so make sure you start practicing and taking this stuff seriously. That's the most important thing you do, just do a bunch of these problems. So I hope I've eliminated some doubts that you might have. Make sure you check out the other example videos for arc length. Thank you and have a nice day.